Welcome to the third session of the Wireless Lab course. In today's session, we will investigate the effect of different modulation techniques on the wireless systems. Mainly, we will see the effect of the noise relative to the order of the modulation of the used modulation format. And also, we will investigate the pattern of the symbol transition on the polar diagrams of different modulation formats and their CCDF and amplitude envelope characteristics. So to begin with, we'll make sure that we access all the devices from the computer that we are using. And we have already shown you how to do this in the previous sessions. So for those of you who do not remember, can refer to those videos from the previous sessions. This is the user interface for the VSG, which we use to generate and transmit the signal. And here the user interface for the VSA, which we will use to analyze the signal. So here the lab manual that we will go through today, and make sure that before you come to the session, make sure that you go through the pre-lab, and particularly in this lab you need to revise the different modulation scheme that you have seen in the lecture. So in the first section of the manual, we are required to investigate the effect of the transmission power on the constellation and EVM diagrams. So basically in this section we are required to investigate the effect of the noise on the signal, because as we increase the transmission power, that means the effect of the noise becomes less and less, and vice versa. So let's move on and implement this first section on our equipments. Now, before we start doing the setups, make sure that the modulation and the RF options are off, as you can see here. And we can start by setting up the carrier frequency. We have three options provided by the manual. You have to pick one based on the bench that you are using. In this case, we will choose 913 megahertz. And also we have to set the amplitude, the transmission amplitude of our signal, which we are required to set minus 60 dBm. And after setting these two parameters, we can now start setting up the modulation characteristics of our signal. So we have to choose the arbitrary custom modulation option, which is here. And before you continue, make sure the digital modulation option is on. So make it on. After that, make sure the multi-carrier option is off, because we will be using the single carrier modulation. So to set up the modulation type, we go to the modulation type here. We are required to set QPSK, which is already selected, I think. As you can see, QPSK is already selected. So it's QPSK here, already selected. I can go back. And now, after having the modulation set, we can adjust the symbol rate, which is specified as 20 kilosymbol per second. And now we can do the filter setup. We are required to use RRC filter, which is root Nyquist. It's already set up here. So root Nyquist selected. We can go back and we can choose the alpha, which is required to be 0.35. You press enter. And now for the transmission part, this is enough. Everything is set up and our device is ready to transmit the signal that we want to transmit. So I will choose the modulation on, because we want to have our carrier being modulated, so we have to choose this option on, and also RF on to allow the transmission to start. In order to receive the signal, we have to do some receiving signal parameter setups. First of all, we have to adjust our center frequency that we used at the transmitter. So we have 913 megahertz here, and then we are required to adjust the span to 40 kilohertz. Now, to be able to see the signal, we have to adjust the range as well from this option here. So I'll put range as minus 20 dBm. So you can see here we can hardly see the signal, and this is because we are transmitting very low power, around minus 60 dBm. So to be able to do some further analysis on this signal, let's go to the digital demodulation setups, and the steps are outlined in the manual. We can go to the measurement setup here and go to the measurement type, which is now operating in the vector mode. We have to select the digital demodulation mode. Now in the digital demodulation mode, we have to set up the digital demodulation parameters properties. So I'll select that one. Under the format tab here, we have to select the proper modulation format that we are using. In this case, it is QPSK, which is already set. As you can see, we have various options here. We just need the QPSK for now, and the symbol rate is 20 kilohertz, which is also already set. Otherwise, you can write it manually. And in the filter, we have to select the root raised cosine filter as our measurement filter, and raised cosine filter as a reference filter, and also the alpha should be 0.35, which is already set. So we are all set now. We can go ahead and start seeing the analyzing the signal from different by using different tools. In the manual, we are required to observe 6 different tools, or 5. So to do that, we have to partition this screen into 2 by 3 grid, which you can do from here, the trace layout option here. We go to the grid 2 times 3. So here we have the spectrum shown, and here we have the polar diagram shown. So we can set the other plots. For example, let's set the constellation in this plot here. We go to the channel 1, and we select the IQ measurement time. And from the IQ measurement time, it's already constellation, but otherwise, if it was something else, we could just go here and choose whatever we want. So in this case, we want the constellation, which is already selected. So we just press OK. And also we need to see the eye diagrams. And in the eye diagrams, we have 2 options. We have the eye diagram. We have the quadrature eye diagram and the in-phase eye diagram. So we will set both. Go to the channel again, select the IQ measurement time, and then this is Q eye diagram was already selected. As you can see, it is Q quadrature eye diagram, similar to this one. Select the IQ measurement time, and from the option here, it's already eye diagram selected, which is here. And in this option, in the last thing that we are required to set is we need to see the error statistics from the symbol per error, which is here. In this the statistics here, we can see different error rates, like the EVM, and also we have SNR as well, and other error statistics are also provided. So now we can adjust the power at the transmitter and see how these figures will be changing. So let's take a note of some parameters here. For example, we can take a note of the signal power that we are receiving from the spectrum. To do that, let's select the band power and show it here. And the easiest way of seeing the band power, we can just right click on the figure and select the show occupied bandwidth. So this is your occupied bandwidth. You can adjust our marker accordingly. Yeah, something like that. So we can see the power that we are receiving is around, it is shown here around 95 dBm. and the EVM, the RMS EVM is around 23. We can take a note of these parameters, of these values. And the SNR is around 11 dB. Now we can let's go and adjust the transmission power as specified in the manual, which we have to increase the transmission power by the step of 10 dB. So let's do that and come back and observe this plots again. So we will increase the amplitude by 10 dB, which is will make it minus 50 dBm. Now we can see some improvement here, and the occupied bandwidth has somehow changed, so we can see here, which is we have some improvements from 95 to 86, 87 dBm. And also we have the eye diagrams looks better compared to before. Even the constellations are getting closer to the ideal points. And the EVM now is also reduced from around 25 RMS to around 7 now. And the SNR is improved to 23 from 11 dB. So as we increase the power, the effect of noise gets less, and the reception of the signal becomes better and better. So we can do the same. We can increase the power again and see. Let's make it, for example, now minus 30 dB. So we are getting the results closer to the ideal results, as you can see from the constellation here. And also the power that received the signal is increased significantly, and the error now becomes 0 point something. As you can see here, is 800 something, but in milli RMS. The SNR has been improved to 41 from 21, 22. So you will observe, when you are performing this in the lab, you will keep increasing the signal to minus 20 dBm by steps of 10 as specified in your manual. And at the end, you are required to estimate the SNR from the spectrum and also calculate the SNR from the EVM. We have already shown you how to estimate the SNR from the spectrum in the previous lab. And also in the lecture, you have been shown the formula that relates the SNR and EVM, so you have to use that formula also. You can take the EVM value, I mean, you can take the SNR value that you have estimated in the previous part of this section to estimate the EVM, and the value that you get, you can compare with the statistics provided on this last plot here. So you can take a snapshot of all these measurements for each transmission power, and when you do your calculations of your SNR and EVM, try to compare them with this and provide your comments.